Hi, my name is Taehoon Kim from Computer Vision Lab at Seoul National University. Today, I'm going to present our work on domain generalization, randomized style perturbations for domain generalization. To start with, I will briefly introduce about what domain generalization is. While deep neural networks show remarkable performances in various tasks, they exhibit severe performance degradation when there exists distribution shift at inference time. This can be a big problem when we deploy the network in real-world applications, since the network can yield unreliable output in dynamic environments. For example, think of autonomous driving. There are thousands of different cities, weathers, and surroundings. It would be a big problem if the driving system acts unreliably due to the changed environment. To deal with this problem, domain generalization aims to train a network that is robust to distribution shift to enhance the applicability of DNS. Our motivation is as follows. In user-style transport studies, it is well known that the characteristics of visual domains are captured by styles of features. If then, it will be able to train a network that is robust to domain shift by train network that is robust to style shifts, because the domain shifts will correspond to the style shifts. Actually, there have been some works with similar motivation. With a similar motivation, existing works attempted to achieve domain generalization by incorporating diverse segmented styles during training. However, there is no guarantee that diverse styles result in style-agnostic networks. Different from the existing works, we try to directly incorporate styles that make network far from style-agnostic in training time, which means styles that can disturb the network outputs. Then, how can we get that kind of styles? The answer is in the adversarial attacks. By adversarially attacking the styles of the features, we get the styles that can disturb the network prediction. And by incorporating these styles, we can train a style-agnostic network, which means robust to the domain shifts. Note that our style augmentation is done at multiple intermediate layer of networks. Also, we run parallel two paths, RASP path and perturbation-free path. The proposed modules are only applied in the RASP path. And also, the network parameters of both paths are shared. Now, let me introduce the detailed procedure of randomized adversarial style perturbations, called RASP. We first compute the style loss, which will be used for adversarial attack to the style. The style loss is computed as classification loss with respect to the chosen target class. Here, Y-target means the randomly selected target classes except the ground truth labels. We select the target class randomly to enhance the diversity and plausibility of augmented styles. After that, we update the styles of the features in a way that the style loss is decreased. Hence, the style augmentation can be viewed as generating styles that deceive the network to classify the given feature to chosen target class. To ensure the plausibility of output styles and avoid the unrealistic style, we only continue style attack when the confidence score for ground truth is above set threshold tau. While RASP generates challenging styles that are helpful to enhancing domain generalization ability, it can degenerate the learning from source domains, since the augmented styles are generated in a way that disturb the representations of networks. To compensate for this, we mix the normalized features of perturbation-free paths and RASP paths. After that, we apply the augmented styles in the normalization of mixed normalized features. By only mixing the normalized features, we preserve the source domain knowledge while taking the advantage of style augmentation given by RASP. Now I will introduce some experimental results for our method. We first evaluated our method in DomainNet, which is the biggest dataset for domain generalization, and it contains the most significant domain shifts. As shown in the table, regardless of network architectures, the proposed method shows remarkable performances compared to the other state-of-the-art methods. Also, it can be seen that the performance gain at challenging domains are more significant than performance gains of easy domains. This illustrates that the proposed method, optimizing worst-case styles, can achieve more significant improvement when there is a large domain gap between source domains and target domains. Similar tendency holds for OPSOM dataset, where the proposed method shows the state-of-the-art performance. This is the results for the POX dataset. As one can see, it shows comparable results to the state-of-the-art methods without using any additional information. We also tested variations of the proposed modules. First, we tested different augmentation objectives. One simple way is to add perturbations in the direction of decreasing the prediction score of the ground truth label, which is referred to as RASP GT. As shown in table, such a direction is clearly outperformed by the proposed scheme. We argue that this occurs because simply decreasing the score of the ground truth label leads to a degenerate example indicating an unrealistic image caused by untargeted star perturbations. We also tested various options related to the NFM modules. When mixup is applied to styles or features instead of normalized features, classification accuracy significantly drops. This is partly because the variations of our mixup strategy fail to benefit from the novel style generation capability of RASP. When NFM is not employed, the accuracy of easy target domains, including art and photo, is significantly degraded. These results support our arguments that NFM maintains the knowledge learned from the source domains. We also evaluate the proposed algorithm by applying our star augmentation technique to multiple different layers in the network. Table demonstrates that the performance of the proposed method varies greatly depending on the location of style augmentation. Applying the proposed algorithm at multiple feature levels is important for successful integration because network becomes robust to style changes in multiple intermediate levels. We also conducted analysis about hyperparameters. Selecting proper hyperparameters is a major issue in domain generalization since the access to the target data is restricted. According to the table, the target accuracies and source accuracies given by the proposed method are highly correlated. This ensures that one can select the proper hyperparameter for the proposed method by considering the source accuracies, which is the available option only with the source data. To conclude, we present the simple yet effective style augmentation technique based on adversarial attacks. Also, to compensate the degradation of learning source domains caused by the style augmentation, we propose the novel feature mixup technique. And lastly, the proposed algorithm consistently shows the remarkable domain generalization ability in multiple standard benchmarks. Thank you for listening.